Hi there, I'm Scott Lowe with ActualTech Media, and thank you for joining us for this RoadCast video. I'm joined today by Mustafa Pinarbasi, who is the CTO and Senior Vice President of Magnetics Technologies at Spin Transfer Technologies. Mustafa, thanks for having us here today.
Thank you, Scott.
Where are we?
We are right now in our test lab where we do the test of the thin film materials and also the chips that we make, MRAM chips that we make in our lab. So all the testing, wafer level testing is done here.
Let's walk a little bit.
Sure.
So what separates you, how is your lab special? What separates you from some of your competition?
One of the key things that we have is we have a self-contained lab, which we can have a very fast turnaround of the experiments and the prototyping.
What are some of the biggest challenges you have with chip development here in the lab?
The biggest challenge that we have is that the MTJ technology is new, and getting the required state-of-the-art equipment is very expensive. And having those tools, having access to be able to do the experiments has been the biggest challenge for us.
What is MTJ? What does it stand for and what does it mean?
MTJ is it's called magnetic tunnel junction. It's a device that forms the magnetic random access memory. So it is the basic element, basic device that forms the magnetic random access memory.
So what do I see in this case behind you right now?
What we are seeing here is actually the wafers that we have processed to do experiments and prototyping. And these are 200 millimeter wafers that has been processed in our fab over here.
And what ultimately will these turn into?
And what we do is we actually have a design for the CMOS part of it that has been done in the semiconductor foundry. And the wafer comes here and we do the last part, that is the magnetic random access memory part in our fab. And we completely finish the wafers and passivate them. Once we passivate them, we can test them here at the wafer level, and then we send them out for the cutting so we can package them as chips. And at that point, it's a full functional memory chip.
And over here I see magnets of some kind, electromagnets, right? What is that?
What we see here is, it's called a ferromagnetic resonance tool. This is actually a tool that's been built in-house. It is a very unique tool because it measures some of the critical magnetic properties of the structures that we are making. And one of the key things here is it measures the response to very high magnetic fields and how it's going to behave. It tells us how it's going to behave as a device once we form the structure.
Very good. And what else do we have over here? Like I see also in here, something looks like it's been designed. It's a circular thing. I don't know what it is.
What that one is that now we have the chips on the wafer. We have many chips, and what that one is that does is it makes the contact to the chips where we have specific pads, and it makes the electrical contact, and then we are able to measure each individual devices on the wafer.
Very good. And we see lots of other tools back here. What are some of the general functions of some of the tools we see back here, and how are they helping you better develop the technology?
So what we have here is actually we have 3 testers that you see, and this one has been the latest one that we have purchased. And what we are able to do here is once the wafers are finished, when they are fully finished, and we can actually do the testing at the wafer level for individual devices, and we can see how they will work as once we actually put them in the product environment. And one of the unique things here is that we can actually, these devices are supposed to be working anywhere from -4 degrees C to 125 degrees C, maybe 150 degrees C. And what we are able to do with this tool is that we can measure the performance of these devices in the temperature range.
Got it. Okay, so you're actually checking to see checking to see how they withstand certain environmental characteristics so they can be put into whatever types of applications your customers are going to choose reliably.
That's right. So these devices have to work negative 4 to 125 degrees C or 150 degrees C. So the specification requires that these devices are fully functional in the temperature range. And these tools help us understand how these devices are going to behave in that temperature range. And when we do the experiments, we get the data, and then we utilize that data to do further experiments and the prototyping based on the data that we receive from the wafers.
Mustafa, thank you for inviting us into your lab for today's discussion.
Well, thank you, Scott.
Thank you very much. And thank you to our audience for joining us for this discussion as well.